Imagine you are buying something online. You check your cart, choose a payment method, and click the button, Pay. A small circle starts spinning. A few seconds later, the screen displays, Payment successful. From the outside, this process seems to have only two events, a click and a result. But what actually happens in the time between? First, the interface packages the order information into a request. This request is sent to the backend system. The system validates the order, checks the user data, contacts the payment service. The payment service then communicates with the bank. Once the transaction is authorized, the system saves the result, reduces the product inventory, and sends a confirmation notification. All of this happens just to create one tiny message. Payment successful. We can place all these components into boxes: front-end, back-end, payment service, and database. But a collection of boxes only tells us what the system contains. It does not tell us who calls whom, what happens first, what happens next, who is processing, and who is waiting. To answer those questions, we need to introduce time into the diagram. Let's arrange each component into a column: the user, the front end, the order service, the payment service, the database. Now, from each component we draw a line straight down. The top represents the beginning of the process. As we move down, time moves forward. An event that happens later will appear lower down. By doing this, we perform a very special transformation. We turn something invisible, which is time, into visible distance. This is the foundation of the sequence diagram. The entities involved in the process are called participants. A participant can be a user, an interface, a service, a database, or an external system. The line dropping down from each participant is called a lifeline. It represents the participant's existence throughout the interaction. But not everything that appears in a request is a participant. The price amount is data. The success status is a result. The pay button is just part of the interface. A participant must be an actor or a component that actively sends, receives, or processes a message. To start drawing, we ask a very simple question: who initiates this action? In this case, it is the user. The user clicks the pay button. The front end receives that action. We represent this interaction with an arrow. The arrow goes from the sender to the receiver. Pay order ID. This arrow is called a message. A message does not just represent moving data. It represents one participant asking another to fulfill a responsibility. After the front end receives the request, we ask the next question: does the front end process the payment itself? It does not. The front end passes the request to the order service. The order service might need the order details. The database returns the order data. Then, the order service calls the payment service. The payment service processes the transaction and returns the result. If the transaction is successful, the order service updates the order status. Finally, the result returns to the front end, and the front end displays a message to the user. This is the happy path, a timeline where everything goes exactly as expected. Not every message demands a new action. Some messages simply return data or results to the previous caller. We usually draw these as dashed arrows. These are return messages. For example, the database returns order information. The payment service returns the payment result, and the order service returns the final status to the front end. However, you don't always need to draw every return message. Keep only the ones that help the viewer clearly understand the flow. When a participant receives a request, it starts working. We can mark this duration with a small rectangle on the lifeline. This is an activation bar. When the order service calls the database, it must wait for the database to reply. When it calls the payment service, it waits again for the payment to complete. Thanks to activation bars, we don't just see who calls whom. We also see who is processing, who is waiting, and how the operations are nested inside each other. So far, the diagram only describes the success scenario. But what if the bank declines the transaction? At this point, the system has two possibilities. Imagine the timeline splitting into two paths. UML uses a frame called alt to represent this. Alt is very similar to an if-else structure. If the payment succeeds, the order is updated. If the payment fails, the system returns an error. Only one of the branches will be executed. Some actions only happen when a specific condition is true. For example, the system only asks for extra verification if the transaction is high risk. An optional branch is represented by opt. If the same group of messages runs multiple times, we use loop. For instance, before checking out, the system checks every item in the cart. Each item's stock is checked once. Instead of drawing the same message over and over, we wrap it in a loop frame. Now let's go back to the pay click. Suppose the payment service has sent the request to the bank, but the response takes too long. The front end assumes the transaction failed. The user clicks the pay button again. From the interface's perspective, both clicks look almost identical. But on a sequence diagram, we can see two distinct requests. The first request is still processing. The second request has just started. If the system doesn't realize both requests belong to the same transaction, the customer might get charged twice. A sequence diagram doesn't magically fix this bug, but it does something very important. It makes the error visible. Many design problems begin as things we have not yet seen. By now, we know how to read a diagram, but how do you draw a new one yourself? Don't start with the tool. Don't start with UML notation. Start with the use case. For example, the user requests a password reset. The system checks the email. If the account exists, the system generates a reset link and sends an email. If the account does not exist, the system still returns a generic message. Before drawing, we break this story into actions. Now, we find the participants who actively join the conversation. Who starts? The user. What does the user interact with? The reset password UI. The interface passes the request to a handler. The password reset service. Where does the service look for the account? The user repository. And who sends the email? The email service. We do not choose the email itself as a participant. The email is just data. We also don't choose the success message. That is just a displayed result. Now, pause the video. Based on the use case we just discussed, try to answer 4 questions. Who initiates the action? Who is the next participant? What should the first message be called? And what could happen differently? Try drawing the happy path first. Then, add a branch for when the account does not exist. Ready? Let's build the answer together. The first message goes from the user to the reset password UI. The UI passes the request to the password reset service. The service looks for the account. The repository returns the result. If the account exists, the service generates a token and asks the email service to send the reset link. If the account does not exist, the email step is skipped. But in both cases, the interface displays the same generic message. And just like that, we turned a written use case into a complete sequence diagram. When you need to draw a sequence diagram yourself, follow these 6 steps. 1. Pick a specific use case. 2. Write the main flow as simple actions. 3. Identify the participants that actively send, receive, or process messages. 4. Draw the happy path from top to bottom. 5. Add necessary return messages and activations. 6. Look for alternative paths, alt for multiple possibilities, opt for optional actions, loop for repeating actions. If you understand the story behind the use case, most of the diagram will build itself. There are a few very common mistakes. Mistake number 1. Letting the user call the database directly. Users only interact with provided interfaces or APIs. They never control the database directly. Mistake number 2. Using a participant-named system. This name is too broad and hides the responsibilities of the internal components. Mistake number 3. Naming messages too vaguely. Processed data does not tell the reader what the real purpose is. Mistake number 4. Drawing every single internal function. A sequence diagram is not a copy of your source code. It should only keep the interactions necessary to understand the use case and system design. A software system usually asks 2 different questions. The first question, what components are in the system? Classes, services, modules, databases. That is the structural view. The second question, when an event occurs, how do those components interact? That is the temporal view. If a class diagram is like a cast list, then a sequence diagram is the movie scene showing those actors interacting. One tells you who exists, the other tells you how the story unfolds. A sequence diagram is not just boxes, lines, and arrows. It is a way to slow down time inside a system, a way to see the conversations that the user never sees. Who starts, who calls whom, who is processing, who is waiting, what happens if a step fails, and what could happen differently. So, when you start drawing a sequence diagram, don't start by memorizing notation. Start by understanding the story. Because at its core, a sequence diagram is just the story of your software organized by time. Sequence diagrams make invisible behavior visible.